is the UEFI Firmware Secure Coding webinar. It's about 9 a.m. Pacific, but we're going to give a few more minutes just actually start it to make sure everyone's online and attending. Hi, everyone. Welcome to the UEFI Firmware Secure Coding for Firmware webinar. I'm going to pass it over to our moderator, Brian Richardson, now.
Good morning or evening or afternoon, everybody. Time is weird after the daylight saving time change. My name is Brian Richardson. I work for Intel Corporation as part of their firmware ecosystem development team. And I'm going to be leading this discussion with a couple of experts in UEFI development. As soon as there we go. The focus of this is going to be on secure coding. So we've had other webinars in the past on the fundamentals of UEFI, and there's a lot of documentation that talks about just generically what UEFI is and how it works. Our focus today is really looking at the best practices for creating secure code. Helping me with this discussion today are going to be a couple of panelists: Trevor Western from Insight Software, Eric Johnson from American Megatrends, and Dick Wilkins from Phoenix Technologies. All three of these gentlemen work in BIOS development. We try to call it firmware development these days, but the term BIOS still kind of sticks around even in the age of UEFI. And our focus today, again, is going to be on these secure practices. So I'm going to start off with Dick. Dick is an associate professor of computer science at Thomas College in Maine. He's principal technology liaison for Phoenix Technologies based in the U.S. His bio is really long. I'm not going to read the whole thing. If you've read a standard on firmware in the past 30 years, Dick probably had some involvement in working on it. but has been extremely involved in UEFI and sits on the board of directors of the UEFI Forum. So Dick, I'm going to start out, since we're talking about security, let's define our threat model. Firmware is typically kind of an isolated single piece of software by itself on a motherboard. So what is the threat model for this, and how is it different from traditional operating system or application software?
Thanks, Brian, for the introduction. The answer on threat model is kind of twofold. One is the threat model for firmware has not been formally defined to date, and that's been recognized in recent times as a big gap. And so the open source community, the specification working group around security, and the UEFI security response team, which I lead, have identified that we really need to create a formal, published, documented threat model for firmware. And we are actively working on that. Everybody has a real job to do in addition to helping out with the UEFI Forum. So it may take us a little while to get there, but we're working on it. That said, as it says on the slide, as applications and operating systems have become more and more secure over time, firmware has become, by default, a really good target. Plus, the fact that firmware is persistent on the machine, and you can wipe your disk and reinstall your OS or whatever all you want, and if your firmware is compromised, chances are it's going to remain compromised, and you may need to, replace your motherboard or something once your firmware has been compromised. So it's a real attractive target for the bad guys out there in the world. So we really need to define a formal threat model, but in addition to that, a lot of what you'll hear in the slides today are driven out of known attacks and known bad behaviors by the bad guys. So go ahead, Brian. Flip the slides. Yeah, there we go. So just assume your firmware is in a hostile environment. It's true, it's a program. It's just a program. It's really software that's embedded in the machine, and it has all the same potential attack surfaces that any piece of software does. So right off the bat, obviously, anything that comes to you as an input needs to be validated. Does this make sense? Is it correct? Is it going to overflow a buffer? All of those things that you would do in any application program needs to be done. Second of all, never rely on security by obscurity. The idea here is, there was a push in the last few years pushing back against UEFI, saying it uses standard C interfaces and is spec'd out thoroughly and has standard callable interfaces. Doesn't that make it much more dangerous? Wasn't it better back in the old BIOS days when we were using processor interrupts and assembly language only code wasn't that giving us much more security? Well, I've observed in recent Black Hat conferences and DEF CON and things like that, where the bad guys will go out and buy 50 or 100 machines and put them in a bank and put software up to attack them and attack for months, attempting to find vulnerabilities they can exploit. So obscuring it by just making it hard or not well documented or whatever is not going to save you. You can't assume that just by obscuring your interfaces or not documenting them, whether nobody's going to find them. So, lastly, on this slide, there's been a move afoot in the industry. Every OEM wants to outdo every other OEM with the fancy whizzy features that they add, and every firmware vendor out there wants to show how clever they are and how many neat features they can add to their firmware. There is a danger in doing that you could end up just adding to the attack surface and the potential holes in your security just by adding all these additional features that are maybe not well thought out, not well written, not written securely, etc. So if you don't need a feature, don't have it. Limit, if you have the capability of doing something, but you're not actually using it, disable it, etc. That's true on every machine at every level, but it's particularly true at firmware. There has been a bunch of work. Phoenix did some work several years ago on protection of firmware using the capabilities of the hardware and compilers and that kind of thing that are out there. There are a bunch of tools and build options that allow for more secure firmware. You should be using them. Many of these have been added to the Atiano Core EDK open source environment, but many of them are not enabled by default. You have to go in and look around and understand what you're doing and enable them and test them. So you should be doing that. They're not enabled by default because they do increase code size and potentially slow things down a little bit, but I think the trade-off for security is probably worth it. And we're not as constrained as we used to be on size of chips to store firmware in and that kind of thing, and amount of memory available to us and all. So increasing the size may be worth it in this situation. Make sure that you enable these during the development of your machine and you leave them enabled in running code. Examples here that we've talked about at Phoenix for quite some time is address-based randomization, making sure that no piece of code ends up at the same address every time you load it. That way it makes it much harder for the people who are inserting code in buffers and that kind of thing to call into running code. Make sure that data is marked no execute, so that you can't execute buffers, etc. And for example, in the compiler space, Microsoft provides in its Visual Studio C++ environment the /GS option, which uses stack cookies and buffer boundary checking and that kind of thing to make sure that the heap isn't compromised and the stack isn't compromised. Again, that tends to get turned off in firmware. It's default on in applications, but in firmware it tends to get turned off. That's probably not a good idea. Those are just some examples, and other tool sets have other switches to do the same thing. Go ahead. But talking about debugging things, you need to be removing any backdoor interfaces that you leave, that you use, like inserting special code in your firmware during the platform debug process and startup that enables USB ports or other kinds of ports on the machine to get in and manipulate firmware and settings and that kind of thing. Don't ship with those things. People will find them and people will use them, and bad things will happen. I do a whole separate presentation on remote management interfaces and baseboard management controllers, or BMCs, and how notoriously dangerous these are and how they can be used as backdoors into a system. And one broken BMC can attack your private network and attack other servers on your network. There have been some really horrendous cases out there talked about. Be cautious of these. There's an effort underway for an open source BMC management tool. We haven't yet convinced them to use UEFI for that, but I recommend, if you're in the BMC business, you consider getting involved in that program. A specific one for coding, asserts. Asserts are a really good tool for catching bugs that should never happen. If you have a situation where you reach a point in your code where you know that this should never ever happen, and if it does, it's a significant failure that should probably reset the box and reboot, then that's a place for an assert. But asserts should never be used for catching errors that are likely to happen or could happen. or for validating inputs. The primary reason is in most production code, asserts compile away and go away to nothing, and they don't do any checking at all. So if you're using an assert for checking your inputs on a subroutine call, for example, the assert goes away and then you're not checking at all. Continuing. SMM, or system management mode, is particularly dangerous. And I use the term SMM here. This is for the x86, x64, whatever, Intel, AMD type processors. But the same thing applies to the ARM processors as well. They emulate this environment. And in particular, the platform initialization specification, we sort of made it agnostic and call it just management mode now, because it does apply to multiple platforms. But anywhere, any code that runs in these highly protected modes is incredibly dangerous. If you as a hacker can get control of the machine at that level, then all bets are off. Nothing in that machine is ever secure again. It can change hypervisors, OSs, antivirus checkers, anything like that. So some really basic hints is your security code reviews should really focus on SMM code, drivers and things that are in there that respond to SMIs, the system management interrupts. SMM code must never, ever, ever call out of SMRAM. Anything that's going to run in there should be in SMRAM. It should never call into an unprotected part of the system, because that could be damaged, and you're running at the higher privilege level, but you're running unprivileged, potentially unprivileged code. And also, you must check your input parameters. You must check a copy of them that's in a protected location, not the location in unprotected memory, because there have been many situations where time of check versus time of use has happened, where you validate the parameter, then it gets changed, then you go back and try and use it, and it's been changed and is now unprotected. Next. Lastly, for my little part here, is protection on things like UEFI variables and other areas of code or whatever. Flash memory protection should be enabled as early as you can possibly do it in your hardware. As early as it can possibly done, those flash protections should be enabled. And also, S3 resume from sleep versus hibernate and boot, is a different code path in many systems, and you need to make sure those flash memory protections are enabled in S3 resume as well as boot and hibernate resume. That we have seen a number of cases where this has not been done properly and have left the systems unprotected. Lock all authenticated UEFI variable regions as early as possible, again, so they can't be stepped on. Set variables read only, if at all possible. That makes sure that any variables that shouldn't be ranged should be changed, can be changed. And most importantly, if someone does change an UEFI variable that may be relatively security innocuous, if you don't have a reasonable fallback for improperly set UEFI variables, then that could be a denial of service attack. Setting a fairly innocuous variable to a setting that doesn't make sense, nonsense, zero, whatever, can cause the system not to boot, and you just create a denial of service. And so don't leave your variables, don't have a fallback and just go, just stop or reboot or whatever because the variable is a nonsense value. Make sure that you can fall back to something that will at least get the system up where you can fix it. That's it.
Okay, it's pretty comprehensive. Thanks, Dick. Just a reminder to the attendees, we will be taking questions at the end of the webinar. If you have a question that comes up now, just go ahead and put it in the chat window, and we're going to sift through those and pick some for the panel to look at the end of the presentation. Up next, Trevor Western works for Inside Software. He's the Vice President of Engineering, and he's head of the Product and Services Security Group. That means he's responsible for implementing security best practices and tools across all the company's development teams. That means he's a great person to ask about the wonders of C. I've been writing C code probably a little too long. My C book was Kerrigan and Ritchie, so I'm a little old school. But C is often accused of being kind of an insecure language, not because it doesn't feel good about itself, but because it's very close to the hardware. And you can make all kinds of interesting design decisions, which some programmers may want to turn into an exploit. So, Trevor, when you're programming firmware, how do you compensate for all the wonders of C and its language insecurities?
Yeah, I think C is a wonderful and powerful language, and it's one of the things that we've all gotten used to. And like yourself, I've worked in C for many years, and I think I've come to accept a lot of the insecurities as being just a normal part of the C language. But it's time to take a fresh look at that and really understand what are the trade-offs and sacrifices we're making in order to have this powerful language. And a side effect is that it's a very dangerous programming language, despite it being one of the most popular low-level systems programming languages in the world. It's one that schools still recommend learning, even with C++ added to it. It's extremely powerful and extremely dangerous, and we have to go back and take another look at the compromises that we've made in the past in terms of the security in this language, its ability to protect itself from bad inputs, and so on. If you move ahead to the next slide, I wanted to talk a little bit more about some of the weaknesses and taking a fresh look at this. So, as many of you know, C has no mechanism to test that a memory pointer is valid. And when you think about this, it's rather shocking. Does the memory pointer really point to an actual memory type as you intended? Is it really pointing at a string? Is it really pointing at the data structure you intended it to? It's amazing that we have a language here that doesn't validate that. And it took me by surprise when I thought about this a few months back, that this is one of the improvements that could be made to C. So with the power of C and the looseness by which you can reference data types, there needs to be some checking in place. And I'll go into a few examples in later slides. It also permits you to access memory beyond the memory that was allocated and assigned to a function. You can allocate a 1 byte into memory and then start modifying and changing addresses beyond that 1 byte. There's no parameters, no boundaries to what you can access. It doesn't control itself. It's a highly insecure language and allows you to do anything. You can mix code and data. You can create a self-modifying program. I would think in the current day and age that would be just blatantly dangerous to do. You can pass function addresses into routines and then manipulate that address to execute a different routine somewhere else. I think we've also forgotten that C is very complex. I gave the example in the slide here of a pointer to an array of functions that return a pointer to an array of functions. That's actually a legal example. And good luck debugging that. And the other thing in there, if you notice, is that these are pointers to arrays of functions. So in other words, this is an array of code that could be executed. It's casually mixing up functions with data again. C is just very casual, very sloppy in one sense. And so we need to take proactive steps to make sure we're respecting the power of C and making sure we're not overstepping the power it has and using it in an insecure way. And one minor point on the bottom, I think the syntax, and we've probably all gotten used to it by now, the syntax has subtle mistakes in it, where you can use, say, an equal sign and an assignment operator. They're just one character different. It's one of the more common mistakes to make in C, and it has a dramatic effect on the results in the program. On the next slide, if you don't mind moving ahead, Brian, you can see some of the results of what C has done in this industry, and I think Microsoft at the recent Blue Hat conference in Israel said 70% of all vulnerabilities were memory safety issues. Now, what they mean by a memory safety issue is that where a program has accessed memory in an unsafe manner. So buffer overflows, page faults, null pointers, stack exhaustion, so on. Use after free or double freeze. I was in a code review last week and we saw someone get confused about what memory they had to access, and they used it after a free operation. So this code seems to work some of the time. The memory after it had been freed still had the same contents before the free operation. So the code appeared to work. There were no symptoms of this bug until someone made a small change in the code, and therefore the memory got overwritten again, and therefore you had a strange error coming up. This is a side effect of C not having memory management capabilities, not having the ability to identify what the type of memory that is being pointed to. So I think C and UEFI, as it's defined now, have a series of improvements that can be made in the way they're handling a lot of the insecurities that are currently in the design of the code. If we can move ahead. So what can we do to fix this? Use tools is the simple answer. C compilers are getting better. As Dick mentioned earlier, turn on all warning options that are possible. Make sure you have the heap checking in place, the GS option that Dick referred to. It's also there in EDK2. You can see stack checking in place. And also ban the use of unsafe C library functions. I think many people on this call will know about the string n functions, that is, adding a length parameter to the string functions is the first step in making them safer. But also in EDK2, there are now a series of secure functions with the S attached to the end of the name, so string length S is available. This actually does some non-destructive, careful examination of the input parameters so that things like destination strings are not destroyed. The memory is not left in some intermediate state if an operation fails. So switch over to the string length S functions for when you're doing strings. And then there's a series of similar functions for other portions of the C library. You can also ban the use of complex functions with variable arguments. I think variable arguments are an attack vector that's just really not necessary. Things like print, which function which has no idea of the number and type of arguments it's going to receive on the stack. Highly dangerous function, or even the install multiple protocol instances, which takes a list of protocols as its arguments. These are just a little too complex and too easy to create an attack vector that's going to actually make an entry point into the code. So on the next slide, ban the use of pragmas and casts that tell the compiler to ignore the warnings or ignore the errors. Casts are fine. Make sure they're intentional and you really understand what you're doing. Pragmas are directives to the C compiler to tell it to ignore the error. Well, this is really, it's like unbuckling your seatbelt. You really want to have it buckled up. You really want the C compiler to actually tell you what it thinks you're doing in that code. And you should go to the trouble of trying to explain to the compiler in the right language, whether that's a specific language for the compiler to understand in a preprocessor directive. Get it to explain the error and get it to understand exactly what it is you need to do to make that code simpler so the compiler can understand it. The compiler is your friend. You should not be turning it off and shutting down the warnings. The second bullet here, I wanted to also mention, and this is something that came up for our internal code reviews at Inside. If you're doing calculations on memory, there's a real strong chance you're getting it wrong, and some of our most experienced engineers are offended by this statement. But it has been proven to be true, especially if someone's using signed integers to do memory calculations, buffer overflows, underflows are very common, and sometimes they're extremely subtle, and they can only be seen through fuzz testing and very intense code reviews. So stay away from memory calculations. It's just fraught with dangers, even for the most experienced engineers. And the final bullet, I'll come back to the topic of tools again. Static code analysis tools are getting better than ever, and they're able to handle a lot of the complexity in UEFI code. And two that we've worked with here at Inside Clockwork and Coverity are widely used in the industry. We've also been pleased with Microsoft's Visual Studio 2017, which has a static code analysis feature. There are some false positives on the Visual Studio 2015, but we're finding a lot of improvements in the 2017 version. So I would recommend taking advantage of an SCA tool, integrated into your environment so that the error output is properly managed, it's tracked as bugs, that it's integrated with your source control system. It has to be something that's in the mainstream of your security activities and part of your secure development lifecycle, your SDL. So one might ask, well, why not switch to another language that's more secure? As many people in the industry has pointed out, every programming language has its weaknesses. There's a great book called 24 Deadly Sins of Software Security, Programming Flaws. And the authors show that several of the security flaws I've mentioned in this presentation can be seen in several different programming languages. And there's also Rust, which is a relatively new language that focuses on memory safety and concurrency. It's quite a great improvement. If you have an opportunity to work in Rust, I would highly recommend it. And there's the link right there. But the overall message you should be getting is that security comes from following a security practice like SDL. It's not the coding language. It's the security practice that you really need to focus on to make improvements in the security in UEFI. And Brian, I think that's my entire message.
Yeah. All right. Thanks, Trevor. And I do want to point out for some of the people that may be into Rust, there is actually a group that's been working on adding Rust bindings to the EDK2 open source UEFI implementation. So I'm glad you've got a reference for that here as well, because there seems to be some interest in the industry in adding that as an option for people who want to write bootloaders or other UEFI applications. Okay, so now we've talked about the threat model for firmware. We've talked about the programming practices. Now it's my favorite subject, which is validation. How do we make sure that we did all the things that Dick and Trevor talked about? For that subject, I'm going to bring in Eric Johnson. Eric is a senior software engineer and security coordinator at American Megatrends. He has 14 years of experience in the industry, working a wide variety of things like embedded video decoders, helicopter training devices, credit card terminals, and payment devices. Now he's working at AMI, is responsible for UEFI security advisories and test tools. So Eric, let's talk about testing. Firmware is kind of an odd validation environment. So how do you check for the kind of security issues that we've been talking about earlier in the seminar?
Well, a lot of people have the impression that it's very hard to do certain types of testing with firmware. And the issue is that the software is coming from so many different hands. So the silicon vendors provide part of the firmware, IFVs or IBVs provide parts of the software. There's open source software included. OEMs add their own software at the end. So you have a bunch of different hands that this is all going through, and unless you have a stable platform to start with, you really can't test anything, because until the system comes up, you can't run your specific module, your driver, or anything like that to test to see whether or not it works properly and that it's secure. So, and then there's also the fact that the setup for many of these devices is very complex, and you can enable and disable different features that may affect platform security in general. If you enable CSN mode, of course, you're going to be able to do things to attack the system that just would not be possible if you're using UEFI only firmware. So there are a lot of different aspects that make firmware very tricky. And as Trevor brought up, one of the most important things to do is to do static code analysis. So you can do this in a variety of ways. You can use tools. Obviously, he mentioned several. There are open source tools like CPP check. And then code review itself is a form of static code analysis. You have somebody who is an expert in that, whatever code you're working on, who reviews your work to make sure that you're not making subtle errors with the syntax of the language, that you're following the specification for whatever you're trying to implement and things of that nature. But unfortunately, that's all human driven. A human has to interpret the results of the static code analysis and take the right actions, and humans make mistakes. And of course, tools make mistakes also. So you may miss issues that can only be found by actually running the code. So in order to do that, you would use dynamic code analysis techniques that in the firmware space have typically been limited only to things like integration testing. But it's actually also possible to do unit testing in firmware, which most people think is just too difficult to be worthwhile. But there are a lot of instances where the security is so important that you really do need to test an individual module and make sure that it's not providing a platform for somebody to infect the system. And I'll talk about that a little bit more. But one of the other things that you can use to analyze your code is a symbolic execution tool. And the way that symbolic execution works is that the tool actually looks at your binary, and instead of passing in inputs into your function or your module or whatever, it replaces those functions with a variable, and it goes through every branch of code and calculates what variable, what value the variable would need to have in order to actually execute that branch of code. So the idea behind symbolic execution is to help you generate test plans that basically provide as much code coverage as possible. And you can also use symbolic execution with fuzz testing to increase its capability. So it's a really powerful tool and can help avoid a lot of the issues that I've seen working with firmware. Next slide, please, Brian. So one thing that I think really enhances the security of the platform is to actually test any code that has been found to be vulnerable in the past. So everybody here has a lot of responsibility that they need to take care of. They're busy. They probably don't have time to go back and add unit tests to their old projects, their old drivers, whatever they're working on. So they need to decide when the best time is to add a new unit test. So when you fix that vulnerability in your code, you should write a test that you can run against the known vulnerable system and actually exploit the vulnerability. And then also, once you've fixed it, run the same test against the mitigated platform and validate that the platform does pass the security test. And this is important because a lot of companies have dozens of projects that they're taking care of. And maybe they just directly import the source code fix from whoever supplied it or fix it directly themselves in that project. But in other projects, they may have to patch. And anytime somebody is manually patching code, there's always the chance that they're going to miss something and, again, introduce a vulnerability through human error. So it's really important to have a test that is known to validate the issue before you can really consider it to be secure. Another thing that needs to be looked at is any code that is crossing a trust boundary. So Dick pointed out at the beginning that management mode is very dangerous. So I would say that it's important to test anything that is run in management mode that takes input from the outside world. Another time to add new tests is obviously when you're writing new code. If you're going to add new functionality, you have to make sure that functionality works anyway. So you might as well create a unit test that can be used by your quality assurance team to validate that the the code meets the specifications, and you can also validate that you're not introducing some sort of security vulnerability by not properly checking inputs and things like that. And then anytime you go back and look at old code because of any bugs, it's the same as developing the new code. You have to validate that fix. You might as well make a test that helps you validate that fix. Next slide, please. So many developers that I've talked to claim that it's difficult or impossible to unit test SMI handlers or really any driver that's running inside of the firmware environment, but that's really not true. You can make a shell application, for instance, that just calls the software SMI and interacts with that SMI handler just like the OS would, just like the attacker would. And so the way that we do that is here at AMI, we try to make tests that cover all of the conditional branches that an adversary might control. So if they're passing in the size of their structure, or let's say they're dealing with storage devices and they're indicating what kind of storage device they want to interact with, anything that changes the flow of code needs to have a test to make sure that you have sane defaults, that if they provide an invalid value, your code handles the error correctly and stops executing or does whatever is necessary to recover from that invalid input. And another thing that we do when we're making our unit tests is that we start with what we consider to be a good request. So let's say that we're testing something that has a data structure you pass into SMM that has several pointers in it. So we'll pass in the data structure itself with a known good pointer, one that should pass all validations, won't cause a page faults or anything like that if copper point protection or some other silicon protection of management mode is enabled. So once we know that works, then we'll modify each pointer in there, and well, actually we'll start with the block itself. So we're passing in a structure. We'll modify the structure, pass in one that should fail validation, and if the code executes, even with a structure going into SMRAM that was invalid, then we know that it's insecure. So then we'll do the same thing with each and every pointer inside of that structure. And as Trevor pointed out, anytime you're dealing with memory arithmetic, you're bound to make mistakes. So anytime somebody allows me to specify the size of the data that I'm passing in, the first thing I always try is 0. Because if you're multiplying that by some constant, you'll end up doing a buffer validation on 0 bytes. Maybe the first byte I give you is valid, but the rest aren't. The rest are in SMRAM or something like that. If you're only checking that first byte because you let me trick you into testing only that first byte, then you're going to end up overriding or reading from SMRAM and doing other things that are dangerous to the platform. So we always check to make sure that any size that's being passed into the SMI handler is being properly validated. If it's an unexpected value, it returns an error or does whatever the default behavior is for that particular module. So obviously the goal in all of this is to get 100% code coverage. And tools like symbolic execution can help you achieve that goal, but it's pretty unrealistic to expect anyone to actually get 100% coverage. It's very difficult on anything as complex as firmware. Next slide, please, Brian. So we have to set priorities, and we should always prioritize, as both of my colleagues have said, anything that has escalated privilege, especially privileges that allow it to manipulate the guest OS, hypervisor, whatever is running on the machine. Then we need to make sure that it's as secure as possible. We need to test it as thoroughly as possible. Obviously, you want to use static code analysis, code review, fuzz testing, unit testing, anything that you can reasonably do to validate that privileged code is very important. And there are actually some tools out there that already exist in the community that I'm sure many of you have heard of that are covered on my next slide here. For symbolic execution, there's, I believe it's pronounced anger, which has been used against Tiano Core and EDK2. And it is a tool that will, again, help you find values to pass into your code to validate or to get as much code coverage as possible. Another one is called Crete, which was developed in Portland, I believe at Portland State University, by a researcher who now works at Intel. And so when he was doing the research, he focused on running it against Linux core utils and also Tiano Core to see how they compared against Anger and Clee. And Clee is another open source tool. I tried to stick only to open source because I'm not advocating any specific tool, but these are all useful tools. There are commercial options available as well if you need somebody to help you get it set up. And of course, not mentioned are tools like ChipSec, which hopefully everybody who is listening to this is already aware of. There are also some tools provided by EDK2. One Intel just announced, I believe last week. Brian, who's on this call, moderating for us, helped write the white paper for that and present it. It's called the Host-Based Firmware Analyzer, and it is actually a tool that will be available as open source in the EDK2 source code repository that leverages, I think it uses Crete, but it uses a symbolic execution, various fuzz testing libraries, and then also basically a hardware emulator to run the firmware. It can actually capture a snapshot once the system is completely set up and ready to run. And then when you run your test, it will, instead of jumping to wherever the firmware was originally and somehow triggering your software SMI, for instance, it will actually put the instruction pointer into the entry point of the software SMI with the test values that you determined were necessary to get the code coverage that you wanted. So it seems like it's a pretty cool tool. I haven't had the chance to play with it. Maybe Brian would be able to tell us more during the Q&A session of this call. But there's also MicroPython test framework, which is in the EDK2 source code. Again, it's a unit testing tool that is similar to ChipSec, similar to the tools I described that AMI creates, where we basically are able to interact with software SMI handlers without having to write the boilerplate code to set up the communication with the code that we're testing. So these tools, especially a Python-based tool, allow you to very quickly get up and running against your firmware and to provide a unit test that you can use in your own QA processes. You can distribute to your customers to help them know that your product is secure. It just depends on exactly what you're doing with your firmware. Next slide, please, Brian. Actually, that might be my last slide. So, yeah. Basically, there are a bunch of tools out there. Firmware is very difficult to test properly, but because we are placed in such a trusted position, it's absolutely imperative that we follow what Dick and Trevor have said about providing a secure environment. And one thing that I didn't mention that I had meant to is another way that you can unit test your drivers. We want to minimize our attack surface for SMI handlers, right? So during boot, there are SMI handlers that are registered that perform functions for third-party option ROMs, etc., help get the platform configured, but maybe they are unregistered before ready to boot event. So in cases like that, what we do here at AMI is we will actually write an additional driver that the sole purpose of that driver is after we know that whatever module we're testing is ready to execute, we will try to hit those software SMIs that are only available during boot time to make sure that they're secure. So you can provide the same kinds of tests that you would from the EFI shell, but the caveat here is, again, to reduce your attack surface, you really need to make sure that you never ever ship any of those test drivers in a production firmware. So it's very important to minimize your attack surface and disable any software SMI as early as possible so that you don't have to worry about someone attacking it after boot. Thank you.
All right, thanks, Eric. Okay, so that gets us through our panelist tips. Thanks to Dick and Trevor and Eric for providing that material. That leaves us with about 10 minutes left for questions. So, Kelsey, did we get any questions off of the audience?
Hey there, guys. Yeah, we did. We are pulling them up now. The chat box just moved around, so just hang with us for 1 second.
While they're getting that ready, keep in mind we will be posting this material with a link off uefi.org for later review, and also have links to some of the tools that we've talked about in the presentation. There must have been a lot of questions.
Hey there. Yes, there is.
So we're dealing with a technical difficulty getting our questions up and running. Eric, I did want to address something while we're waiting on those with the host-based firmware analysis tool. The neat thing about that tool is it actually allows you to do component level testing for individual PEI or DXE drivers. So it's kind of an isolation environment, and it allows you to run things like Peach Fuzz or CLE on a different set of interfaces. So it essentially is an EDK2 stub environment you could drop your driver into. So it gives you a way of essentially unit testing a component before it disappears into the myriad of drivers that you end up incorporating into platform firmware. So the main thing we want to see people do with host-based firmware analysis is they're developing a new component, be able to do individual unit testing on that prior to integrating it into a complex mess of third-party code and the rest of the firmware infrastructure.
So the question I had about that is I assume you're running against a specific hardware emulator in that case?
We're actually not in that case. So something like Excite, which we're still working on open sourcing, which is an SMI-specific environment, is based on hardware analysis because it is designed to take a hardware-specific component and essentially simulate it before you have hardware. Because most of the people in the audience have worked on some piece of early hardware that is about as stable as a three-legged table. It's not quite ready to go, and so you're never sure if it's a hardware issue or a code issue that you're dealing with. What you do with host-based firmware analysis is you're really trying to pick out the kind of things that were highlighted as security issues, the buffer overflows, the bad implementation of APIs. And that's the sort of thing that, is really more what I call abuse testing. So you're doing more negative test scenarios in that case. And the hardware configuration at that point doesn't matter as much as the way the code is structured or executed. So it doesn't matter if you're setting the bit correctly. It does matter if you're setting the bit safely. And so it's really more of a, exercise all of the poor practice type of test before you try to drop it in to an environment. Whereas something like a simulator-based environment like QEMU or Wind River SimX is more about, am I configuring a thing to a particular configuration? That's why it differs from a tool like ChipSec, where ChipSec measures the artifacts of the system. ChipSec is an integration runtime tool. It says, did I configure the system properly? Does the configuration have a known exploit or a known bad behavior? Whereas something like host-based firmware analysis says, am I sanitizing my inputs? Am I keeping memory safe?
Thank you so much, Brian. And we finally got over a little tech hurdle there. Our apologies. But one of the questions that was asked was how to avoid maliciously crafted inputs. including buffer overflows to inject malware.
So who wants to grab that one on the call?
Yeah, avoiding is essentially impossible because you have to take the inputs you're given. On the other hand, clearly you have to validate them. So avoiding buffer overflows, for example, you need to, as we talked about, using the secure and safe string handling, buffer handling, copying things. You never use the values supplied by the user for the size of buffers, how many bytes to copy. You make sure that you always copy the buffer, the amount of space that you have in your buffer. And also, for like the cross-site scripting kinds of things and all that, you need to validate the buffer content as well. And in the odd chance that you do make a mistake, then the things like the GS switch or similar stack protection and buffer protection kinds of things will at least allow you to detect that you have run over and did damage, and you can take proper steps to recover at that point. Others have comments?
No, I think that's exactly right. You just can't trust anybody because you never know what the attacker is going to do. They have the opportunity to decompile your code and see exactly what you're doing. They will find any weakness that you have in there.
Yeah, we've actually observed, talking about what the bad guys do, we've observed them going to OEM sites and downloading versions of firmware and comparing them and looking for what decompiling and looking at the code changes, looking for fixed security vulnerabilities, and then going to old versions of the firmware that are still alive in the field in customer sites and customer hands and attacking those machines. What amounts to 0 day for them.
Great. Thank you for that. And another question that came through is it felt that Rust has useful application in EDK2 given the number of external pointers and global pointers in state?
Yeah, I'll take this one because there's a member of my team, Stefano Sotelo, who's working with the open source community on EDK2 to try to expand the use for Rust. We've seen a lot of people look at Rust as for a starting point for a lot of things like bootloaders, and generally trying to fill the UEFI application space. We're still trying to figure out how that fits into the environment for developing lower level code like DXE drivers. But it's something that we really are wanting to see more experimentation with in open source. So there is a separate community that's been working on doing Rust bindings for writing applications, and we're now looking at if there's an opportunity for someone to move that work into EDK2. So that's really more of a kind of an open source workflow question, which I don't want to bog down the rest of the panel with.
Okay. And then let's see, we have another question come in from the audience that is, how to sign UEFI firmware volumes? Are there tools available?
Yeah, that's actually a pretty common practice. There's a white paper on tianacore.org. If you look in the documentation section, that's specifically the use case of how you do code signing. And we do actually, that's one thing that we hadn't noticed in here because we're talking about programming practice. We didn't cover signing, but we do highly encourage, all in caps, signing of the final output, like the updates that are delivered to platforms. Delivering a firmware update unsigned is really it's a path to pain and suffering.
I would assume that all of the independent firmware vendors would be able to help each of their customers take care of signing, whether they have white papers on the topic or tools provided. So I would definitely recommend that you ask your firmware vendor for help if you need that.
Okay, great. Thanks, guys. And we probably only have one more time, or time for about one more quick question because we're already pushing past 10 here. And so, panelists and moderator, if there's any final key takeaways that you want to leave the audience with for secure coding, what would maybe your top 3 be?
Well, this is Trevor. I would add one on top of that, that there are no quick fixes to secure coding. There's not one magic button you're going to be able to hit and say, this is it, I'm now securely coding. You have to start with a secure coding practice, as several people have mentioned already, and select probably the top 3, top 5 practices out of an SDL and implement those product-wide, company-wide. I wish there was a quick answer to how to fix your secure coding and what the top 3 tips might be, but the fact is there is not an easy answer to this. This is going to take effort and diligence, the use of tools that are designed to make security improvements, and it's the practice and policies inside of the company that really need the first big update. So that's the number 1 for me, is updating the practices used in engineering to develop secure code and make sure you're properly following the secure development guidelines that are out there.
Yeah, I don't have a lot to add to that, but just quickly, make security kind of the number 1 thing that you're thinking about. That make it a policy in your company that the first thing you think about is security. Even consider internal security bug bounties, that kind of thing. Make it a priority, make it something that everybody thinks about every day.
As somebody who used to write a lot of testing code, I'm just going to say be mean to your code. I know we all like our jobs and our products, but people, once they receive your product, if they're an attacker, they're going to be mean to it. So try the methods they use to attack and break your code before it ships.
All righty. Unless anyone has anything else to add, I think that wraps it up for our UEFI Secure Coding for Firmware webinar. Thank you so much to all of the attendees and to our moderator and our panelists. And thanks for tuning in, everyone. Take care.
Thank you.
Everybody.
Thanks. Bye-bye.